countries undergo rapid urbanization and expansion, the demand for infrastructure only continues to rise. To meet this demand, much of the world, including these emerging regions, rely on Portland cement, a material used in many infrastructures, from towering skyscrapers to local gas stations and even the homes we live in. However, Portland cement production has a heavy environmental cost, contributing to around 5 to 7% of global greenhouse gas emissions and energy waste from its production. For developing nations striving to build resilient infrastructure while managing environmental impacts, this reliance on traditional cement poses a challenge. In Brazil, for example, cement production increased from 39.4 million tons in 2010 to 88.5 million tons in 2017, being the fifth largest consumer in the world. There is, however, still hope for a more sustainable alternative: geopolymer concrete. By using industrial byproducts like fly ash and enhancing durability with fibers like nylon and polypropylene, geopolymer concrete has the potential to meet construction needs with a reduced carbon footprint. In this video, we'll explore how this innovative material could help transform infrastructure in developing countries, paving the way towards a more sustainable future.
Geopolymer concrete represents a new class of sustainable materials in the field of construction. First introduced by Joseph Davidovits in 1978, geopolymers are based on aluminosilicate materials, essentially compounds rich in aluminum and silicon, that bond together in a unique three-dimensional network. This structure forms through a process called polymerization, which occurs when materials like fly ash and metakaolin are combined with alkaline solutions. Unlike Portland cement, geopolymer concrete doesn't require the intensive heating process that produces significant CO2 emissions. Instead, it uses raw materials that are often industrial byproducts, such as fly ash from power plants or blast furnace slag from steel production. This allows geopolymer concrete to reduce greenhouse gas emissions while effectively recycling waste materials into durable construction components. With this versatility, geopolymers can be tailored to fit specific needs based on factors like availability and cost. For instance, high alumina or high silica materials such as natural minerals, clays, or waste products can all be used to create geopolymers. The choice of materials directly influences the concrete's properties, making it adaptable to a variety of applications, from structural concrete to fire-resistant coatings, and even waste immobilization. Already, geopolymers have been used in innovative projects like the University of Queensland's Global Change Institute in Australia, where they support large suspended floors with structural strength and sustainability. Studies have shown that geopolymer concrete has excellent mechanical properties, high durability, and can reduce the global warming potential by as much as 61%. In this way, geopolymers not only present a promising sustainable alternative to Portland cement, but could also become key to advancing construction in regions aiming to reduce their environmental impact and build resilient infrastructure. In countries like India, where fly ash is produced in high quantities, more than 40% of the fly ash generated each year remains unused. Reports from the Central Electricity Authority, Government of India, state that between 2010 and 2014 alone, India generated around 613 million tons of fly ash, with 255 million tons left unutilized, equivalent to more than half the area of Lakshadweep Island. This only highlights the urgent need for a more productive use of this material. By utilizing locally abundant resources such as fly ash, geopolymer concrete offers a sustainable alternative to traditional Portland cement and significantly reduces carbon dioxide emissions whilst providing communities with durable infrastructure. For nations like India, Nigeria, the Philippines, and several other countries where affordable housing and infrastructure are priorities, geopolymer concrete offers a path to economic growth and environmental sustainability, creating a more positive future for their rapidly developing countries.
Research was conducted to create and test geopolymer concrete samples with varying quantities of fibers. The quantities of each material used per batch is shown on the screen. Materials included were fine and coarse aggregate, fly ash, blast furnace slag, water, an activator or binder made of sodium silicate and sodium hydroxide, along with superplasticizer, nylon and polypropylene fibers. These materials were mixed carefully to form geopolymer concrete cubes, adjusting the fiber quantities to observe their effect on the concrete's properties. These samples were then killed and tested in batches of 3 cubes each at an ambient temperature for 7 and 28 days, or in the oven for 6 and 24 hours. Compressive and pulse velocity tests were then completed using the machines shown on the screen to measure performance metrics like compressive strength and resistance to cracking. Fibers such as nylon and polypropylene can play a significant role in the performance of geopolymers. These fibers improve the concrete's tensile strength and reduce its likelihood to crack. Tests conducted show that when these fibers are incorporated into a geopolymer mix, it performs better under stress. Of course, there are challenges to consider, such as cost and availability, but the potential benefits make the use of fiber worth researching further. The results revealed that adding fibers to geopolymer concrete improved its mechanical properties, especially tensile strength. High fiber quantities enhance crack resistance, indicating that fibers play a significant role in reinforcing the material. Results also show that increasing the quantity of polypropylene fiber resulted in a decrease in compressive strength. However, surprisingly, had the opposite effect on samples containing nylon fibers in ambient conditions. Oven tests produced much higher results in general compared to ambient tests, and the compressive strength was highest when no fibers were added to the mix, which is expected. On this note, the compressive strength of the concrete samples with no fiber and ones with nylon fiber in oven conditions were on par to that of traditional Portland cement. Moving forward, further research will focus on optimizing fiber content, improving mix designs, and evaluating the material's long-term performance under various environmental conditions. As a result, geopolymer concrete could one day become a mainstream sustainable option in global construction. Geopolymer concrete, of course, has its challenges. Issues like standardizing production, managing costs, and tackling technical barriers require further research. Ongoing efforts need to be done to improve the mix, especially with fibers, and to evaluate how it performs over time. Further research among universities, governments, and the private sector will be key to pushing these boundaries so that one day sustainable materials like geopolymer concrete may be at the forefront of construction. Thank you for watching. For more information, check out our references, and don't forget to comment below your own thoughts on the idea.